The problem states the torsional pendulum undergoes oscillations in the horizontal plane, such that the angle of rotation measured from the equilibrium position is given by this equation. Determine the maximum velocity of point A located at the periphery of the wheel while the pendulum is still oscillating. What is the acceleration of point A in terms of t? So let's think about what the question is asking. First, it is telling us find the maximum velocity of point A, and then it says what is the acceleration of point A. So based on the information given to us, let's consider how we would solve or how we would approach such a problem. Well, the first thing we notice is it gives us the theta as a function of t, which is simply the angular position as a function of t. And the second thing that's given to us is the radius, which is 2 feet. So now let's use this information to determine velocity of point A and the acceleration of point A. The first thing we notice is how can we get the velocity? We're talking about circular motion, so this specific equation will be very helpful, which is velocity equals the radius times angular velocity. Now, we don't know angular velocity, but we can calculate it using the following equation. If we get angular velocity, we do the derivative of theta, which is the angular position, with respect to time. And this will give us angular velocity. Furthermore, another equation is, if we want to calculate angular acceleration, we can do that by doing the derivative of angular velocity. So now let's start solving this problem. First, let's do the derivative of theta here, which will give us 1.5 times sine 3t, and that will be our angular velocity with respect to time. Now, let's get velocity instead of angular velocity by multiplying this value with the radius using v equals r times omega. And we know that the radius is 2, so we find v, which is the velocity value, by multiplying these two and simply getting 3 sine 3t as our function. Now, here's the thing. It is asking us maximum velocity. How can we determine maximum velocity from this function? Well, let's think about what this means. We get the 3, and we have the sine 3t. If I were to plot sine 3t, it would look like this, with a magnitude 1 to -1. So what this means is 3 times this function will always equal something that is 3, or it could be 2, it could be 1, but never greater than 3. So v in this case is smaller than or equal to 3. I also just want to clarify really quick, when I drew this this function here, this is simply sine 3t. If I were to plot 3 sine 3t, then it would look like this. We would erase this and make the amplitude 3 and -3. That's the whole point. This is the amplitude, and this always has a value -1 to 1. Therefore, we conclude that Vmax is equal to 3 feet per second. Now, let's do angular acceleration. How do we approach this? Well, we already figured out omega, which is our angular velocity. All we need to do to find angular acceleration, like I previously mentioned, is take the derivative of omega. And let's do that now. Oh, but before I do that, let me make a correction here. This is not supposed to be sine. This is supposed to be cosine. Because when we take the derivative, the sine turns into a cosine. So that will be 3 cosine 3t. Okay, but the plot is the same because we're dealing with a sinusoid. So this plot looks like this. So if I plot cosine 3t, it's the 1 to negative 1. This should be fairly straightforward. So now, getting back to here, taking the derivative of this function here, we get, so cosine turns into negative sine, so sine 3t with a negative in front of it. And then using the chain rule, we do 3 times 1.5 to get 4.5 sine 3t. So this is our, let me write that a little neater, right here. So this is our function for angular acceleration. So the thing is, the question is not asking us angular acceleration. The question is asking us acceleration. This means that we need to convert this into some coordinates that we're familiar with. In this case, since we have angular, or we could say circular motion, we want to use nt coordinates, the normal and tangent coordinates. So if the motion sort of looks like this, and this is our point A here, we want the n coordinate in this direction. So this will be n, shown with this unit vector. So it will be u of n. And we will have the tangential coordinate that looks like this. This will be ut. So the thing is, we have some nice equations to convert angular acceleration into acceleration in the tangential direction and also acceleration in the normal direction. And these equations are the following. So for tangential, we have r times angular acceleration is equivalent to tangential acceleration. And for normal, we have the angular acceleration squared times r, which is the radius. Then this gives us the value we want. Well, let's do it then. So plugging in the values, we get, we have r as 2 times negative 4.5 sine 3t. And for omega squared, we have our omega up here. So that will be 1.5 cosine 3t squared times our radius, which is 2. Now to top it off, we express the acceleration in terms of these coordinates, or in terms of functions that are in line with these coordinates. So we say acceleration is equivalent to negative 9 sine 3t multiplied by ut, which shows us the direction. You can sort of think of this as the I hat, the j hat, and the k hat that we have been previously using. And we have plus, because the sign of this is positive, we have 4.5 cosine squared 3t, and this is multiplied by u sub n, which is in the normal direction. And this concludes the question.